we can start now since we have two resource persons tonight. So we will start at the exact time. First, good evening, everyone. Thank you all for joining our program again. On behalf of the organizers, I would like to welcome you all to the fourth day of One Day International Webinar on Science in the 21st Century. I'm Dr. Lalnunmawii, and I'll be your host for this session. Last night, we had a distinguished speaker, Professor R.K. Thapa, a retired professor from Department of Physics, Mizoram University, who delivered an informative talk on photofield emission study from metals and its applications. And tonight also, we are really lucky that we are going to have two research persons, Dr. Esther Lalnunmawii, Department of Biotechnology from Mizoram University, and Dr. K. Vanlaldinpuia, Department of Chemistry from Pathunga University College. Both young, talented, efficient, and dedicated in their profession, not only in teaching, but in research field as well. And they even had really great contributions in their respective fields. Both their topics for tonight are also quite relatable. We are really grateful to both of our esteemed resource persons for being with us here tonight on such a short notice, despite their busy schedule. Let me have an announcement first to all our dear participants that our program is streaming live on Government Certificate College official YouTube channel in case if you have a problem in using Zoom apps or signing in. And if you have any queries regarding the presentation, you may drop your questions in the chat box even while our speakers are presenting. And those who are joining us through YouTube, you can also put your questions in the comment section. We will later open a short interaction time at the end of the talk, and you can also unmute your microphone that time and ask the question directly. And I want to add that you can ask your questions in Mizo, especially for the students, as I think all the attendees here tonight are okay with that. So please feel free to ask any doubts you have, as this program is organized for you, so that we can all make the utmost use of this program. Okay, without taking much time, let me have a brief introduction of our first speaker for tonight, Dr. Esther Lalnunmawii. By highlighting some of her academic background and achievements so far, Dr. Esther Lalnunmawii is currently working as an assistant professor in the Department of Biotechnology, Mizoram University. She completed her bachelor degree in zoology and master degree in biotechnology, both from Northeastern Hill University, Shillong, and finished her doctoral degree in the Department of Biotechnology, Mizoram University. She even cleared UGC CSIR net exam while pursuing her master degree. One scholar completed MPhil under her supervision, and right now she is the supervisor of 5 PhD research scholars with her main work related with environments and molecular biology. She has several publications and one ongoing research project as well. Tonight, she will present a paper with the topic Impact of Single-Use Plastics. Dr. Esther, thank you once again for accepting our humble invitation. So with that, let me invite Dr. Esther to give her presentation.
Thank you, Dr. Lalnunmawii, for the very nice introduction. I really don't deserve it, but thank you anyway. So yes, my, when I got the invitation for this international seminar, I was really, really honored. And I would like to thank the organizers as well as all the people involved here. So the second speaker for tonight, Dr. Mapwe, is actually my senior in NEHU. So I talked to him and asked him, what are you going to present about? And he was saying something about plastics. So, I'm really also interested in the environment and what plastics have done to them. And my field is in microbiology as well as molecular biology, which are related to to the environment only. So, that is why I will be presenting something upon plastics as well. So let me first try to share my screen. Is my screen visible?
Yes. We can see it. Yeah.
Okay. So I'm going to talk about the impact of single-use plastics tonight. So the topic for the whole seminar is about trends, in major achievements in the 21st century. So coming from biotechnology background, you might have expected me to talk about maybe, one of the greatest discoveries like the CRISPR technology and how RNA editing or how, editing of the gene is potentially one of the most powerful tools today. But seeing that we are from different backgrounds of science, I would like to go for something a little bit more simple and which all of us can touch upon, like, in our daily lives. That is why I have chosen the impact of single-use plastics tonight. So I am trying to, okay. So first of all, I think we all know what plastics are. They are synthetic or semi-synthetic materials which use polymers as the main ingredient, right? And we know that they are very, flexible. They can be molded into various shapes, and they are so useful in our daily lives. I think if you just look around your room or look around your house, you'll find many things that are made of plastics, right? So they are made typically made through human industrial systems. They are derived from fossil fuel-based chemicals. And recently, there have been, some plastics which have been made from renewable materials and also some, recyclable plastics as well, right? And there are different types of plastics depending upon the, the density, depending upon the material, the chemical from which they are made. But we won't delve into details of that. And what is really interesting is that they've been classified based on the size as well. So macroplastics being the biggest among the classification, we have mesoplastics, microplastics, as well as nanoplastics, all right? So depending upon the size, the particulate size, of the plastics, they have been classified as such, right? So like I've mentioned before, plastics are like, a part of our daily life, right? So you can find them in your kitchen, you can find them in your, your makeup products, you can find them as, nearby, maybe your water bottle might be a plastic bottle, right? You can find plastic toys, you can find, motor parts that are made of plastics, right? They're everywhere, right? But tonight, the topic which we will delve upon is single-use plastics. And these are the items which are intended to be used only once, right? And after using once, you have to throw them or recycle them. And according to a study, done by the United Nations, the rate of recycled plastics is quite low. Okay, so this is one data which I got. In Europe, the rate of recycling plastics is around 30%. In the US, around 90%. And in a developing country like ours, there is almost no recycling, okay, sadly. And 91% of all the plastic which is in use and which is being produced is single-use plastics. And the amount of, pollution that has been generated is so much. And according to a study by the World Economic Forum, the production of plastic is set to double over the next 20 years. So it doesn't look like, we have a very bright future. So the single-use plastics that we see in daily life may include straws, water bottles, right? Earbuds, polybags, etc. I think you can see these in our daily lives, and we might have been using them also. And according to the United Nations, again, a study, the most common plastic, single-use plastics, which were found in the environment were studied. And surprisingly, to my surprise, we must be smoking so much, because the most single-use plastic that was found in the environment consisted of cigarette butts. Okay, next comes plastic drinking bottles, caps, food wrappers, etc. Okay, so there is so much plastic around us. And let us go into a little bit of the history. Since the 1950s, the production of plastic has been so much that it has outpaced, the production of almost every other material. And in 2015, 400 million tons of plastics were produced, and 36% of those total production is for plastic packaging. Okay, and much of the plastic which is produced and which is designed to be thrown away, that those single-use plastics are, have been produced so much. Okay, and in 2015, it was studied. The study showed that 141 million tons of plastic packaging waste was produced in 2015 alone. And upon further studies in recent years, this number has been sadly slowly increasing, right? So what happens to plastic waste? 9% is recycled, okay? 12% is incinerated, which means it is burned, and 79% of all the plastic waste have been studied to be, just dumped in landfills and then into the environment, okay? So this is what is happening around us. So, these so much plastic and so much production, so much use, when it is burned, this burning of plastics releases gases, toxic gases like furans, dioxins, mercury, PCBs. Okay, there is actually a spelling mistake there. I'm sorry for that. And this has posed to be a threat to vegetation as well as human as well as animal health. Okay, so everything in the environment is related. We depend on one another. We depend on plants. The plants depend on the soil, etc., etc. Okay, so everything in the environment is related and interrelated, and we are dependent upon each other. So once these toxic gases, these toxic chemicals are released into the environment, it goes and goes and finds itself in the in our system as well. All right. So dioxins, they may settle on crops, and they may enter our waterways and then enter our food chain again, and then enter us. Okay, I don't think anyone wants plastic in their system, right? Okay, I won't go much into the food chain, etc. And phthalates, which have been added to plastics to provide the flexibility as well as softness to plastics, these are actually endocrine disruptors, and they are associated with so much of health problems. They can cause fertility issues, and they can have neonatal impacts on babies. They can cause allergies, they can cause asthmas, etc. Okay, so, and burning of plastic waste can increase the risk of heart disease. It can aggravate respiratory ailments. Okay, it can cause nausea, headaches. It can cause rashes. It can cause damage to the nervous system, which is not something that anyone would want. And burning of plastic also releases black carbon soot, right, which contributes to climate change and air pollution. And I think every one of us has listened enough about climate change and air pollution, so I won't go into the detail again. All right. So what is the impact, or what are the impacts of mismanaged single-use plastics? So it is studied that if we don't improve our consumption patterns as well as our waste management strategies, then by 2050, around 12 million metric tons of plastic litters in landfills and the environment would have been found. All right. And these, we are talking about single-use plastics only, mind you. It would have environmental impacts, like we have said. It would definitely have health impacts, right? And anything that has an environmental impact as well as a health impacts will contribute to economic impacts as well. All right. So not only environment, not only health, but also economic impacts. All right. So if you are not still convinced enough that we should, go away from single-use plastics, I will give you 9 more reasons to refuse single-use plastics. First of all, they are made from fossil fuels. And as we all know, fossil fuels are considered to be non-renewable sources of energy, right? And secondly, these single-use plastics leave a very, very huge carbon footprint, okay? And they will be here for hundreds of years. They will survive longer than us. And they are not, once they have been disposed of, then, they don't contribute much to the environment or to, the food chain or anything, right, other than doing harm. So you don't want them to stay in the environment for hundreds of years, right? And only a tiny bit of only a tiny percentage of the plastics in general is being recycled. And number 5, it leaches toxins into your food and drinks. I think you might have seen in your mineral water bottles, okay, crush bottle after use. The reason is that plastic packaging, right, that bottle has a certain lifespan, has an expiry date, okay, after which it will start leaching whatever chemical it is made of into whatever liquid is in it, okay. That is why it is written crush bottle after use, okay. And number 6, it causes hormone disruptions and cancers. 7, it pollutes the oceans. You might think we are so far from the ocean, but the ocean impacts us all. So we still have to care, right? It will kill marine animals and birds. It has been killing and disrupting the marine ecosystem so much. And if you look at the terrestrial animals and birds also, these animals and birds have also been impacted by plastics, right? And number 9, we have talked about how they enter our food chain and the different health concerns and issues that they are causing, right? Okay, let me go to the next slide. Okay, so I have just kept some pictures of the damages that plastics have done to marine life. There are lots of pictures on the internet which you can find, but I've just kept a few of them. So how long will single-use plastics item be around? So the plastic bottle that you are using for drinking water, for drinking your mineral water, would probably outlast you. Okay, so for 450 years, a plastic bag may last up to 20 years, depending upon the thickness of the plastic bag. A cigarette filter may last about 10 years. Styrofoam will just stay like that forever. You see, these plastic items might just break down, okay, but they will never degrade. Okay, they will just stay on and on and on. Okay, they will just break down to smaller pieces, and they will continue to do their work and continue doing harm to whatever environment they are present in. All right. Okay, so I think most of you might have seen this. These are the 17 Sustainable Development Goals which have been proposed by the United Nations in 2015. So these 17 goals are set to be, the UN has proposed to achieve by 2030, all right? So you see, plastic pollution as well as the use of plastics can be, can affect many of the different goals which the UN has set here. So like climate action, life below water, life on land, responsible consumption, production, etc., clean water and sanitation, etc. Okay, so there are so many goals and there are so many impacts, negative impacts on the goals which the UN is trying to attain for our betterment, right? So the priority actions, let us take a look at the priority actions to minimize single-use plastics. First of all, waste management systems have to be improved, right? That is a must. At the home level, okay, the individual level, at the family level, at the community level, at the government level, right? Waste management systems have to be definitely improved. And secondly, promote eco-friendly alternatives to phase out these single-use plastics, right? We need to go for alternatives. You just can't take something from somebody and not give an alternative. That is not fair, right? And thirdly, we have to, educate our consumers to make more environmentally friendly choices. And fourth, enable voluntary reduction strategies. This has been also done by Mizoram government some time ago. And number 5, ban or introduce levies on the use and sale of single-use plastic items. Okay, so these have been done and carried out by different governments around the world. Okay, and I think these amongst all of these actions, improving waste management and promoting more eco-friendly alternatives are something which which are very which will be how should I keep this? I think I can use Mizo language, right? So, heng te hi inge til kan ti the ingal le mo well some taka ke ni po ina kan vatel ve the ingal na ni English ya. Okay, so I will continue in English. And here we have been talking about single-use items. We can go for reusable alternatives instead of going on with single-use items which we know are going to cause us harm right now and in the future as well, right? So there have been studies on the impact of national bans as well as the impact of the government levying taxes and fines, right? But we talked about a little bit about renewable or biodegradable bags a little bit in the beginning. So you see, these biodegradable bags, I don't really know about the current situation, but from the research papers which I have read, all right, so these biodegradable plastics don't automatically degrade in the environment because they require a certain set of conditions, okay, a certain temperature. So if that temperature or if that certain condition is not met, that plastic which is supposed to be biodegradable does not degrade, okay? So there is some trick there. And there has been case studies in different countries on different governments have been trying to reduce the use of single use plastics as well as plastics in general, and different countries in Europe, Asia, Africa, and the Americas have tried different, techniques in order to reduce all of these, but the consumption is still sadly increasing. Okay, but now we are living in a world of COVID. We have to talk about, the need for surgical masks, face masks, latex gloves. We need face shields. We need PPE, etc. Right? We can't live without those in these days. So, in a world of COVID, okay, how are we to deal with these, this plastic pollution, right? I think Dr. Mapwe is also going to be tackling this problem. So this is like an opening remark, all right? So the World Health Organization estimated that, in the early onset of the COVID-19 in, 2020, 2019, and 2020, per month, 80 million medical masks, 76 million examination gloves, as well as 1.6 million set of goggles were required per month, okay, in the world. Just imagine the amount of waste that would generate. I'm not saying that we shouldn't be using those. We are in a world in which we are forced to use that, right? So what I'm suggesting is that we, as scientists, as people in science, okay, as a citizen of the world, okay, what can we do in order to, tackle the problems which we are facing right now, right? That is the question, the very, very big question. So the amount of plastic waste which is generated worldwide since the outbreak is estimated to be 1.6 million tons per day. That is a lot, right? Very much. So here I have just given a world map, which have been color coded. So these countries, okay, if you can see the amount of face masks, discarded per day, okay, this is how much, each country is, discarding, okay. So according to a study by Peng et al., 8.4 plus or minus 1.4 million tons, okay, this is just an estimation. This, this much of pandemic associated plastic waste have been generated from 193 countries as of August 23rd August 2021, okay. So these include hospital waste, right? These includes face masks, personal, PPE, gloves, etc., etc. Okay, and thousands and thousands of tons of these are released into the ocean, into our water bodies. Okay, and we know that this COVID-19 pandemic is surely going to have a short-term and long-term effect. During the first half, maybe around 2020 and 2021, you might have seen, articles and short clips about how nature is coming back, right? How nature is reclaiming itself again, how birds and wildlife are reclaiming because human beings have been forced to stay indoors, right? So we know that the total emission declined in different countries, right? Environmental pressure was lesser, it went down. These are all positive effects, right? But something which I'm afraid of is like, how should I keep this? Let me give you an example. So let me take myself as an example. Suppose I am on a diet. Okay, I feel that I should go on a diet, and I have been starving myself because I want to, right? And I have lost about maybe 5 to 7 kilograms. But then, there is a change there, right? But then I suddenly break my diet and go back to my old habits like I was before. And if I start taking even more than that, what is the use of that diet, right? So this particular pandemic has so much of effect on the environment, on the economy, on human health, right? And the kan tuna kan lo insum to na mo tuna tilcha anga lang kan lo ti mek to te kha kan old habits sa kan let le ani chan ama aina sa khan khoveli kan ti chiang em ti kha zona om thei chu ni ta ni. I hope we all understand. I am leaving you here with questions and what to do. Okay, so is there anything you and I could do? Definitely, the answer is yes. And we have to do it, right? We have to think about what we can do also. Because, microplastics, we have learned about the different types of plastics depending upon the size, right? So microplastics have been found in the Arctic snow, okay? Snow which was actually falling. And, the deepest part of the earth is the Mariana Trench, and plastics have been found there as well. Okay, so we have to do something before our whole world is overrun with plastics, and before there is no, before it we actually come to a time when it is too late. Okay, so every little action counts. We have to opt for our own eco-friendly products and say no to single-use plastics. We can bring our own bottle, we can carry our own bag, we can opt for other reusable alternatives, right? So those small changes will really help. You might think that you are only one person. If I am the only one doing it, and if others are not doing, there won't be any change. But I'm telling you, the amount of effect that a change in a single person's life can do is like a ripple in the ocean. Okay, it can create big waves. So all of us working together, even though we are just a tiny part of the global community, then you see, if we do our part, okay, that will definitely lead to a positive change in the environment and in the world which we live in. Okay, that is what I believe in. So this is a photograph which has been taken by me and by some other people from around Mizoram. It is beautiful, right? I know beauty lies in the eyes of the beholder, but Mizoram is very beautiful in my eyes. Okay, so the disposal of plastic waste have had so many bad effects on the beauty of Mizoram as well. Okay, now I'm just going over the more aesthetic things. Okay, so huge amount of plastic waste can be seen to gather in piles, and I am someone who is who appreciates nature and loves going on a walk and just going on some random hike in some random trails. Okay, so I have seen so many things, and I usually carry a trash bag so that I can pick up whatever I get. Okay, so this is a picture. These are pictures which have been taken by me on some of my hikes. Okay, so it is sad to see so many so many plastics which are littering here and there on places which would have otherwise been very scenic with and I would have been able to take nice pictures, but then it has been ruined by plastic waste. So I call this the sad rock because it looks very sad with this headband of plastic waste. Okay, very sad to see these things. See, all of these have been taken by me on my walks. Okay, so it is high time that we do something, right? So you might say that there have been advances in science in which there are microbe which can degrade plastics, right? So but we can't just rely on those. Okay, microbes are very small. Even though they can do very big things and miraculous things, we still have to do our part, right? So again, this is one picture which might have been very nice, except for this plastic bottle here, which was picked up later by me. Okay, I did not leave it there. So I think you must have seen scenic beauties here and there all around Mizoram. Okay, so we need clean water for survival. We need clean air for survival, right? Is it that life was reportedly life came from the ocean, right? So are we dumping everything into our original home? Okay, is this supposed to be the circle of life? I don't think so. I hope not. So I think we can safely say that it is high time that we stop plastic solution. You and I can make a difference. You and I can make a better today, and you and I can definitely help to create a better future, right? So I think you might, yes. Okay, so I think you might have heard of the 3 R's. Almost done. Okay, so reduce, reuse, and recycle, but I have included one more R, refuse. Okay, so but the most important thing here I feel are refuse and reduce. Okay, that is why I've given in such big letters here. So we know that demand is equal to, because of the demand the production will increase, right? So the consumers play a very key role in the production of all of these single-use plastics and other plastic materials. Okay, so for the future generation, we have to change our habits today. All right. So this is one cartoon which I used to see during my teen years. This is from Captain Planet, and like Captain Planet used to say this one catchy phrase, "The power is yours," right? So you and I have the power in our hands to change our world today. Okay. So I think Sir Mapuya, Dr. Mapuya will be talking more about how to, recycle plastic waste. So I think with this, I can safely end my presentation here. These are some of my references, and thank you very much for listening.
Thank you so much, Dr. Esther. It was a really nice presentation and very informative also. Thank you for reminding us the need of reducing the use of plastic in our everyday life and its harmful effects to the environment, in a simple and catchy way, I should say, and necessary steps we need to take to have a cleaner environment. Thank you so much. Now we will open a time for interaction with our resource person. If anyone has a question, you can ask directly by unmute yourself, unmute your microphone also if you want.
I think we're all waiting for Dr. Mapuia's presentation on how to recycle plastic waste now.
Okay, if there is no question, I think that clearly indicates, if no question indicates that our speaker is clearly presenting and clearly explain everything, I think, in her talk. So we will proceed according to our program. Next speaker for tonight is Dr. Vanlaldinpuia, as I have mentioned before, who is an assistant professor in the Department of Chemistry, Patunga University College. He completed his bachelor, master, and even got his PhD degree in chemistry from Northeastern Hill University, Shillong. He also cleared a CSIR UGC NET exam in 2009, and he had also numerous publications in debuted journals. And in addition to that, he already completed 2 major projects funded by UGC, and currently he has 2 ongoing major projects worth of 53.46 lakh and 49.86 lakh funded by SERB DST with a project titled Chemical Characterization and Biological Studies on the anthelmintic property of indigenous medicinal plants of the Mizo tribes. And the second one is carbohydrate-derived organocatalysts and their application in organic synthesis. Right now, he is the main supervisor of 1 PhD research scholar, and he also co-supervises other 2 research scholars. And tonight, his topic will be reducing plastic waste from the environment, new challenges for the 21st century. Dr. Mapuia, it's a great pleasure to have you here. So if you are ready, you may now start your presentation.
Okay, thank you so much, Miss. I hope my slides is visible.
Yes, we can see it.
Okay. Okay, thank you so much. And thank you so much to Government Stewardship College for inviting me to be a part of this international webinar. I really appreciate it. And it is something which I will cherish and remember for a long, long time. And a very, very big congratulations to every one of you, to the principal, to the teaching and non-teaching staff, and to all the students and other stakeholders for getting grade A in that last cycle of NAC assessment. It was a very, very big achievement, and it was your hard work and dedication which make it possible to accomplish that Herculean task. So congratulations to each and every one of you once again. There are so many challenges in the 21st century, especially when you look at it from science and technology point of view. And one of them is reducing plastic waste from the environment. And my topic for tonight will focus on that, and I will concentrate more on the chemical recycling of one of the most widely used plastic, polyethylene terephthalate, or PET in short. So using agricultural waste, biomass-derived heterogeneous catalyst. So plastics seems inescapable these days, as they are everywhere. And it was reported recently that they are now even showing up in some of the world's most remotest places, such as Mount Everest and Mariana Trench, the deepest point in the ocean. And it has now become a global concern. The first fully synthetic plastic was bakelite, invented in 1907 by Leo Bigland. And the large-scale production of plastic started in 1950s only, but now it has become one of the most widely used polymeric material. Since 1950s, the productions of these plastics increased by almost 200-fold annually, from 2 million metric ton per year in 1950s to 359 metric ton in 2018. That means in 2018 alone, 359 billion kilograms of plastics was produced in that year alone. Okay, so that means for each and every one of us, currently I think there are around 7.8 billion people in the world. So for every person, 46 kilogram of plastic was generated in that year alone in 2018. And it was estimated by the end of 2015 that all the plastic waste ever generated from the virgin materials and recycled plastic was 6,300 million tons, out of which 4,900 million tons were cast off in the landfill. So approximately 80% of the plastic waste ever generated were abandoned in the natural environment. And at the same time, it was also estimated that 8 million tons of plastics enter the ocean every year. And by 2040, 1.3 billion tons of plastics will be deposited in the environment. So this huge increase in plastic production justifies the rise in demand, as it is used in almost every sector. So it is used in, for example, plastic packaging industry, in building and construction, in textile industry, consumer products, transportation, electrical and electronics, and industrial machinery. So it has so many uses, and as a result, there is a huge increase in its production, and that production rate has increased every year. And in natural condition, plastics are almost indestructible as they are non-biodegradable. And as I have already said, it is it is one of the most demanding environmental issues right now. So with its exponentially increasing consumption, combined with its non-biodegradability, the accumulations of plastic waste in the environment rises steeply. So tremendous efforts have been put forward by the research community for its proper disposal. Currently, there are 3 methods of plastic waste removal. The first one is landfilling. And then we have incineration and pyrolysis. And then the third one is recycling. Landfilling occupies space, we know that, and it is already at the premium. And incineration and pyrolysis provide energy in the process, but that is at the expense of the emissions of toxic fumes and gases such as carbon dioxide. So recycling is now the most practicable and most environmentally friendly method of plastic waste management, and the only method which satisfies the concept of green and sustainable chemistry. And there are many different types of plastics, and they can be classified either by the chemical structure of the polymer's backbone or by the chemical process used in their synthesis, their physical properties or the qualities of the product. As I have already said, I will highlight some of the recent development in the chemical recycling of one of the most widely used plastic, which is polyethylene terephthalate, or simply known as PET. So this is PET. So this is PET bottle, okay? Mineral water bottle is PET bottle. PET is the third most extensively used thermoplastic polyesters, and it accounts for 13% of the global plastic output. It has a very high tensile strength, and they are chemically and thermally inert, and it is very safe. It is not harmful to the human body. Okay, it has glass-like lucidity, high strength to weight ratio, and they are very, very cheap. And because of these unique properties, they are now an unparalleled food and beverage packaging material. And it is also used in textile industry as a synthetic fiber and insulating films in video and audio tapes, etc. And apart from that, of all the plastics that is ever generated that is ever synthesized in the laboratory, it is the cheapest and easiest to recycle, but only about 54% of the total production is recycled worldwide. And currently, there are 4 different ways of chemical recycling of plastic waste. The first one is primary recycling, in which involves reprocessing of the uncontaminated low-grade industrial waste generated by the manufacturing industry. Industry plastic and losium surta chalo khalom tathin botol chalo the khalom tathina botol and sim suda example hang a chalo ho khal suat la lo ho kha and the form le chu and reprocess tiang khan and recycle train chu primary recycling and this one. Then we have secondary or mechanical recycling, which involves separations of the PET or the plastic waste from the contaminants, followed by size reductions and melt filtration to produce new material. This is the most widely used technique in plastic recycling. But one limitation is that it results in the degradations of the plastic properties. That's why it is often referred to as downcycling or downgrading or downcycling. Then the third one is tertiary or chemical recycling of PET waste. And this is a very well adopted and sustainable recycling method in which PET is depolymerized to its monomer or secondary value-added products. And then we have quaternary recycling, which involves the recovery of the energy contents of the plastic using incineration or pyrolysis. So among these 4 methods of plastic waste recycling, only the chemical recycling technique meet the criteria of sustainable development. It is because it results in the regeneration of the monomer from which PET polymers are built, and that monomer can be repolymerized to get the polymer, that PET material again, like that it can be recycled again and again using this method. So in recent year, different chemical recycling techniques such as ammonolysis, aminolysis, hydrolysis, glycolysis, and methanolysis were developed and investigated. Ammonolysis results in the formations of terephthalamide. This is the structure of terephthalamide. Then hydrolysis gives terephthalic acid. Okay, this is terephthalic acid. And depolymerization of PET. Okay, this is PET bottles by methanolytic method yielded dimethyl terephthalate. That is dimethyl terephthalate. Then glycolysis. Glycolysis means depolymerizations of PET bottles using ethylene glycol gives PET monomer. And this is the monomer from which PET is synthesized. hemia chang hian tuna water bottle kan ti ho jong so and synthesize the ani. Okay, so among these techniques, glycolysis is considered as the best method of recycling, not only because it regenerates the monomer from which PET is synthesized, but also it is the least capital intensive process. And it is usually carried out at a reaction temperature of 170 degrees Celsius to 300 degrees Celsius. And complete depolymerization could not be achieved without catalyst even at a high temperature and long reaction time. And because of that, different types of catalysts were explored and investigated for this transformation. So traditionally, that glycolysis of PET was carried out using metal salts or metal oxides, and these are some of the examples, some of the catalysts investigated for the PET waste recycling. When zinc manganate tetragonal spinel, the first entry, okay, when this catalyst is used at a reaction temperature of 260 degrees Celsius, the reaction was completed within 1 hour, yielding 92% PET monomer. But if you use zinc acetate at 196 degrees Celsius, the reaction is completed within 3 hours, giving almost 86% yield. But when you use that same catalyst, that zinc acetate, entry number 9, okay, if the reaction is carried out at 190 degrees Celsius, the reaction takes 8 hours to complete, and it gives only 62% yield. So there is a huge differences when you decrease that reaction temperature by just 6 degrees Celsius. Then like that, you can use this sodium carbonate also. So the reaction done at 190 degrees Celsius gives 62% yield within 8 hours of reaction time. But the same reaction, the same catalyst gives 80% yield of PET monomer in 1 hour reaction time, but at 196 degrees Celsius. So in investigation, factors such as temperature, time, reagent loading, catalyst loading, and particle size influences the outcome of the reaction. So it was from this investigation, it was found that these factors affect the outcome of the reaction. And for the depolymerization of PET using glycolytic method, we can use zeolites also. These zeolites are a class of aluminosilicates minerals, which are usually composed of silicon, aluminum, and oxygen. And they have microporous structure. We can see it here also. Okay, we can see it here in this the schematic representation of this beta zeolite. So they have microporous structure, and they are mainly used as an absorbent and as a catalyst for different types of transformations. So when we employ these zeolites as a catalyst, the reaction was carried out at 96 degrees Celsius, and after 8 hours of reaction time with 6 equivalent of ethylene glycol and 1 weight % of the catalyst loading, beta zeolites gives 66% PET yield, while gamma zeolite gives 65% PET yield. So these are some of the results which had been done by the international community. So we can use ionic liquids also. So it was employed, it was investigated for the glycolysis of PET. And these ionic liquids are salts. Okay, they are salts, usually having a melting point below 100 degrees Celsius. For example, table salts, that sodium chloride, the melting point of that sodium chloride is 801 degrees Celsius, 801 degrees Celsius. But these ionic liquids, they have a very low melting point. So these are considered as green solvents or green catalysts And the advantages of ionic liquid is that they have unique features such as thermal and electrochemical stability, and they have low flammability, and their structure can be adjusted easily. These structures can be adjusted very easily. So til chỉ tam tak kan siam su thei kimi khi kan du kan thak ko la ti kan modify ko la oh ti kan chỉ tam tak kan siam su thei chu structural adjustability and nature. So many different types of ionic liquids were employed for these transformations, and here I have given some examples. If you look at this entry number 1, BIM-OH, this is 1-butyl 4-3-methyl imidazolium hydroxide. So using that and using 10 equivalent of ethylene glycol at a catalyst loading of 5% reaction takes 2 hours to complete at 190 degrees Celsius, giving 71% yield. And the best result is obtained with BIM BF4. This is 1-butyl 3-methyl imidazolium tetrafluoroborate. Okay, and the reaction give 95% yield in less than 1 hour, but the reaction temperature is 255 degrees Celsius, which is quite high. And they have employed nanoparticles for glycolysis of PET also. The main advantage of using nanoparticles as a catalyst is that they can be recycled again and again, and they give high yield and short reaction time. See, most of them gives excellent yield. Here, the lowest is 90%. The rest, 100, 99, 96% like that. So when we use gamma ferric chloride, this is gamma ferric chloride, okay? So the reaction was completed within 1 hour, but the reaction temperature is 300 degrees Celsius. It gives more than 90% yield. And this is iron oxide boosted multi-walled carbon nanotubes. So using that one at 190 degrees Celsius, PET monomer was obtained in 100% yield. Very good yield. But one limitation, the limiting factors is that the preparations of these nanoparticles are very problematic. Sometimes multi-steps has to be employed, and sometimes you have to use harmful chemicals for the preparation. So every catalyst, every procedure has some limitation. And recently, organocatalysis was also explored, and it was investigated for that same transformation for the glycolysis of PET, and they are quite effective, giving up to 91% yield. So this process, that means glycolysis of PET using organocatalyst, it becomes more efficient when strong bases are used. For example, DBU and TBD. Okay. And among these two, DBU, this one is more basic compared with DBD. But this TBD show more efficacy. It is a better catalyst when it comes to the depolymerization of PET. And that is attributed to the bifunctionality of TBD, as you can see here. Okay, it has two functional group, this one and this one. This biofunctionality of TBD is believed to play a crucial role in increasing the rate of the reaction. And a mixture of like the ania rope we got this. Nakina po mizo drink a switch ang kati na zilai hosing. Sapo ando thing hopa sapo anin lo of fupissima te poni Italian te poni Japanese te poni hipela ho. Emi te huina han zirchi na hin hi ingwangin ye hemi te pani si ma hin ingwangin hui jok hinge chok di kan zirchi. han ena chuta chuan TBD hi thazo kani an tia inge chan di khan zir chiang ne chuta tang chuan reaction mechanism atang ten chi sang tre han zir chianga calculation theoretical calculation te por han tia khami tang khan tiang kha mu chu ka kha nakina research sapona ti lunga chu mi thil mu chu dan ania hi ro pui tak zit setani kha so a mixture of TBD and methyl sulfonic acid is also used. Okay, as you can see here, and the depolymerization process was completed when you in less than two hours when you use this mixture, giving 91% get yield. So as I have already said, there are some limitations for all the reported procedures, and some of them are these I have shown here. The first one is high cost of the catalyst. Okay, for example, this organocatalysts, which I have already shown, they are quite effective and they afford bed monomer in excellent yield, but they are very expensive. For example, the TBD, just 5 grams of TBD costs more than $100. So it is very, very costly. Okay, then the preparations of ionic liquids and nanoparticles, as I have already said, require several steps, and sometimes corrosive chemicals has to be employed for their productions. And apart from that, high toxicity of the catalyst, long reaction time, and high temperature, metal contaminations in the final product, low yield and poor selectivity of the monomer, and tedious purification process are some of the limitations of the reported procedure. And so to address those things, recently we reported biomass waste derived as a recyclable heterogeneous catalyst for PET waste recycling. The reason why we choose this biomass waste as a source of a catalyst is that as it is of waste origin, it is cost-free. It is free of cost. Mananailaw ni siya. Oh, kan catalyst betuan mananailaw. And it is environmentally friendly, and the preparation procedure is very, very simple. We just have to dry it, and after it is dried, we burn it and we collect the ash. That's all. It's very easy. And the possibility of resolving waste problem with another waste is very challenging. That's why we carry out this reaction. And every year we have generated lots of waste, not only plastic waste, but also agricultural waste and food waste, etc. The global production of agro-waste biomass is estimated at 998 million tons, with an expected increase rate of 5 to 10% per annum. And many of these waste ended up in landfills, and which pollute surface and groundwaters. And when they amalgamate it with the soil, it can produce greenhouse gases. Okay, it can produce greenhouse gases such as nitric oxide and nitrous oxide. Though large quantity of this biomass waste were used for the production of biogas, biochemicals, biofuels, bioabsorbents, biofertilizers, etc. Transformations of this waste into value-added products could greatly reduce waste from the environment. So with that in mind, and with the aim of finding greener route for PET waste recycling, and to reduce the overall cost, the present study was carried out. So this is the paper which we published recently. Here we use orange peel as a catalyst. So we collect the orange peel, we wash it thoroughly with water to remove all the contaminants, to remove all the impurities. Okay, with distilled water, we wash it thoroughly. And after that, we dry it in sunlight or in a hot air oven. And after that, we burn it and we grind it to a fine powder and we sieve that one. Then we collect that ash. So we use this ash, okay, this is the ash for glycolysis of PET. The reaction was carried out at 190 degrees Celsius with 16 equivalent of ethylene glycol at a reaction temperature of 190 degrees Celsius. And the reaction is completed in 30 minutes also, but the best results was obtained with 1 hour of reaction time. And one advantage of this catalyst is that it could be recycled and reused for up to 5 cycles. Kan recycle thế này chứ. Sự thật này mình kan man zo at dangatan kan manglet foi nga lai kha kan han test about kan test alwin chứ. Okay, it could be recycled and reused for up to 5 cycles. And then this is the reason why we used orange peel as a catalyst. Then we also investigated bamboo leaf ash as a catalyst. Bamboo leaves were collected, okay, and as before it was thoroughly with distilled water. And we follow the same protocol, and we collect the ash, okay. So the ashes were collected, grind it to a fine powder, and sieved it. The reaction was carried out with 28% of BLA, with 16 equivalent of ethylene glycol at reaction temperature of 190 degrees Celsius. And the reaction takes 3.5 hours, 3.5 hours, giving 83% bed yield. So bamboo is one of the fastest growing and highest yielding natural resources, we know that. And this is the reason why we choose it. And coming to the next slide, this part is very important, but it may be very boring for some of you because this is the technical part. Anin omang mo kasi lawa amaro su anin pon lautur from ula san su hi poi mo sia. DLA kan tite OPA kan tite kai eng bangin nge an okay. So to find out the active components of those catalysts, those ashes, we perform a series of investigation using different techniques. And the first one is X-ray fluorescence analysis. This analysis was used to find out the chemical composition of the compound. So from this data, we can see that BLA was found to contain silica as the major component. This is silica, SiO2. The concentration is very high. It is 76%. Okay, that is the major component of bamboo leaf ash. Then, apart from that, several other metal oxides, such as potassium oxide, calcium oxide, sulfur trioxide, etc., were also present in varying amount. Okay, so next we used FTIR spectroscopy to detect the functional group present in the catalyst. So this broad vibrational band at 3,442 centimeter inverse is assigned to the OH stretching vibrations of water molecule, which may be absorbed in the catalyst. Okay, and peaks at 164, 1641, and 1446 were assigned to CO stretching vibration, or the CO bond in metal carbonates, and the peak at 1082 and 796 may be due to the presence of SiO bond. So this IR spectroscopy is used to detect the presence of functional group in a compound. Then we use this powder X-ray diffraction method, this technique, to study the crystalline nature of the catalyst. And we compare that result with the ZCPDS reference file. This strong characteristic peak at 21 2 theta and 26° 2 theta are assigned to silica. Okay. And likewise, several metal oxides and carbonates were detected in different concentration in the catalyst. And we use this, the surface area, to calculate the surface area of the catalyst. We use BET method, and the average pore size of the catalyst was calculated using BZH model. And the average pore volume, pore diameter, and surface area were calculated, and it is given here. Okay, this is the pore diameter, and this is the surface area. It has a very high surface area, and the pore diameter is the average pore diameter is 13.6, 13.7 nanometer. So it is mesoporous. It has mesoporous nature. It has mesoporous characteristic. Then we use this NRZ, this dispersive X-ray spectroscopy, to detect the elemental composition of the catalyst. And this EDX method of analysis disclose the presence of silicon, oxygen, calcium, potassium, etc. And this thermal gravimetric analysis, TZ analysis, was used to study the thermal stability of the catalyst. We have observed here an initial weight loss of about 6%. It is probably due to the loss of water molecule. It is probably due to the elimination of water molecule from the surface of the catalyst. Okay. Then here we have observed another weight loss, okay, at around 600 degrees Celsius. This may be due to the decompositions of carbonaceous materials. But if you look at it carefully, the overall weight loss is about 13% only. Okay. It demonstrates the thermal stability of the catalyst even at a very, very high temperature. Temperature sunk 1000 degrees Celsius above 13% loss. Then we use SEM and TEM analysis, okay, to study the morphology of the catalyst. And the SEM, A and B are SEM images, which reveal the spongy nature of the catalyst. And C and D are TEM images, C and D, okay? These are TEM images, and they show different size distributions of the catalyst with a diameter ranging from 10 to 30 nanometer. And then this one is XPS analysis. So we carried out this analysis to find out the elemental composition of the catalyst. And it reveals that silica, oxygen, carbon, calcium, and potassium are the major components of the catalyst. So after characterizing the catalyst, the depolymerization product were then analyzed using different technique to confirm the formations of the desired product. So we carried out HPLC analysis in a reverse phase column using a mixture of methanol water at a volume fraction of 70 to 30 as a mobile phase, and so and so. Okay, so this is the crude product. A is the crude product. So it shows 3 measured peak at a retention time of 1.8. This is 1.8 minutes, 3.4 minutes. Then this is 6.3 minutes. Okay, so we have observed 3 measured peaks. And these 3 measured peaks correspond to ethylene glycol. The first one is due to ethylene glycol. The second one is due to PET monomer. And the third one, this one at 6.3 retention time, is due to PET dimer. We compare this result with commercially available products to confirm the formations of the desired product. So this is C is ethylene glycol, then D is the recrystallized product. So we recrystallize this product. Okay, this PET crude was recrystallized, and we have observed this peak in the HPLC data. Then this is the commercially available PET. Okay, so to confirm the formations of this desired product, all the results were compared with the commercially available products. So, and here this one is the nuclear magnetic resonance spectroscopy, the spectra. The first one is proton NMR spectra. The second one is 13 NMR spectra. So as you can see, these hydrogens shows peaks at these hydrogens, the high aromatic hydrogens shows peak at 8.129 parts per million. Then for OH, it is at 4.97, something like that. Okay. So this is the NMR spectra to confirm the formations of the desired product. Carried out that analysis. And then this is the IR spectra of the IR spectra of the recrystallized PET. Okay, so this is due to OH. This is due to the presence of methylene group CH2. Okay, and like that. And this is the carbonyl use this technique to detect the presence of the functional group present in the compound. And we have proposed this reaction mechanism. Okay, the reaction mechanism for that PET depolymerization. And with BLA, it was assumed that the oxides and carbonates of some of the metals present in it are the polymerization. Okay, so in the first step, the anionic site, here we have the anionic site, O2 minus. This is the cationic site. Okay, so the anionic sites abstract proton from the ethylene glycol. And that results in the formations of a nucleophile through hydroxyethanolate. This is the nucleophile which is formed in the first step of this reaction. Then that nucleophile attacks the carbonyl carbon center of the ester bond, as shown in step 2, to form a tetrahedral intermediate. Okay, so that is the second step. And in the third step, the ester bond cleave in the chain. That this ester bond cleave, and that cleavage reduces the PET polymer, the PET polyesters, into lower fraction. So as you can see here, the process is reversible process, and a chemical equilibrium exists between the oligomers, the dimers, and the monomers. So an optimum condition is needed to get the best possible result. And we also carried out the effect of aided colors on the catalyst efficacy. And we carried out these depolymerizations of different PET color bottles. And as you can see, all the reactions were completed within 3.5 hours of reaction times. And most of the color separates out during the crystallization process. And if there is any remaining pigments in the final product, that can be removed by the additions of activated charcoal during the crystallization. So as you can see here, this is the red. This is coming from red PET. Okay, that is before decolorization. But after the decolorization, we get this one in UV spectrophotometer. And as I have already said, the most important feature of this catalyst is that apart from that, it is free of cost. It can be recycled. For BLA, we recycle it up to 4 cycles, but we have seen a gradual increase in PET degradation time. So in the first cycle, it takes only 3.5 hours, but in the second cycle, it takes 7.5 hours. In the third cycle, 16 hours. In the fourth cycle, it is 21 hours. So there is a gradual increase in PET degradation time. And apart from that, we have seen a slight decrease in the bed yield as well. This may be due to the leaching of the catalyst active sites during recrystallization and recovery process. So before, with fresh catalyst, the percentage of potassium was around 21%. But in EDX data, but here there is no potassium now. Okay, so it is that potassium is completely removed from that catalyst now. I think it is like that. So it may be due to the leaching of the catalyst active site during the recrystallization and that recovery process, that there is this kind of gradual increase in PET degradation time and slight decrease in PET yield. So anyway, so these are my research scholars. I thank them for their dedication and hard work, and financial support from SHARP, CSIR, and UGCR greatly acknowledged. And I would like to say once again, thank you. A very big thank you to the organizer for inviting me to this conference. So that's all from my side. Thank you so much.
Thank you, Sir Dinpuia. It was a really nice and clear presentation. Thank you for enlightening us with such interesting and informative topic. For some of us who don't know, Dr. Dinpuia specialized in organic chemistry. So some part of his presentation may be a little bit chemistry, a little bit hard to catch for some of us. But I hope from what both of our resource persons are presenting tonight, we are again aware about plastic, its uses, harmful effects, and its recycling process, including biomass waste recycling process, like he mentioned, by using different eco-friendly precursor material and its reusability also. And if there is any question, we will open an interaction time for that from our participants. Okay, I think there is no question right now. I think our presenter, Dr. Dinpuia, explained everything clearly, and I hope you understand. And I wish you best of luck, both of our resource persons, for your ongoing projects, your work as well, and for your future. And thank you once again, both of our resource persons, for being with us tonight. With that, we've come to the end of tonight's session. I hope you all find it worth attending. Once again, our heartfelt thanks to both of our resource persons for sparing their valuable time with us, and to all our dear participants, my colleagues, and our friends from various colleges, PUC, BHU, and Hatiel Champai, and Beauty College, MZU, and other participants from various streams. I hope I mentioned it all. If not, please forgive me. And our respected principal is also here with us, who always gave us his support in every program we organize. Once again, thank you so much for patiently staying with us till the end of our program. We will be looking forward to see you all again tomorrow night at the same time. Till then, stay safe. Good night, everyone. Lalnunmawii, good night. Oh, Dr. Esther.
Good night. Good night.
I don't know.
Lalnunmawii.
Hey,
No, come, I start my
Single.
presentation.